Okay, this is test 350, version 1, exam. 1.1. A one-sample test statistics defines a procedure for assessing the consistency of the data instead of the null hypothesis, and we evaluate this evidence using a p-value. This question basically asks the p-value associated with the test statistics can also be considered a random variable. So this question is basically asking whether it's a random variable or not. And it is indeed the random variable because p-value is calculated based on the sample data. And if you have a different sample data, you will have a different p-value, right? So since it will depend on the sample data and different sample data will give different p-values, it will be random variable. So the answer is true. Okay, this question asks, did researchers obtain a sample of size n equals 11 from their respective populations, both known to be normally distributed? In study 1, the researcher has knowledge of the population standard deviation, while in study 2, the researcher lacks knowledge of the population standard deviation. Okay, and it must be estimated. Both studies aim to construct a 98% confidence interval. So since study 2 does not have a clear, does not have a known standard deviation, this will lead to t-distribution. Normally, if you're given that this known popular standard deviation, you'll use t-score. But since it is unknown, you're going to use t-distribution, and then the t-distribution has a heavier tails compared to the standard normal distribution, which will lead to a larger critical value. So, therefore, it is indeed true. So the reason is basically unknown standard deviation, heavier tail, unknown population standard deviation, which will lead to t-distribution. T-distribution usually has a heavier tail, so it has a larger number of critical value. Question asks, in a survey to ascertain the favor presidential candidate among eligible U.S. voters, the nation's electoral college system plays a pivotal role, blah, blah, blah. As part of this study, 500 random set registered voters from each state are polled about their voting choices. The sampling design employed in this survey is stratified random sampling. Okay, this question asks basically whether you remember the definition of stratified random sampling. By Google, stratified random sampling is dividing a sample from a large population into smaller groups. So we have a large population called eligible U.S. voters, and then we're dividing into 500 random registered voters. So this is indeed stratified random sampling. So the answer is true. Okay, this question asks, in a consumer study evaluating the taste preferences of different coffee blends, and researchers are investigating the influence of various factors, including coffee roast level, brewing method, and the coffee bean's country of origin. And one factor that is beyond the researcher's control is participants' experience with coffee. This diversity with coffee experience could introduce variability to the study, so the researchers decided to use randomized block design experiment. Okay, so the question asks, in this scenario, the blocks of the randomized block design would include all combinations of coffee roast level, brewing method, coffee beans in country of origin, and participants' experience level with coffee. So this question asks you basically, you remember the randomized block design. By Google, a randomized block design is a restricted randomized design in which experimental units are first organized. So experimental units are first organized, and then the treatments are assigned at random. So if you include all of these variables, this would kind of defeat the purpose of using the randomized block design experiment. So our variability comes with the diversity in coffee experience. So you put coffee experience as the block, and then depending on that, you can randomly assign, the other variables like brewing method or coffee roasting level. This is why the answer for this question is false. Okay, this question asks the power associated with the statistical hypothesis test is stated to be 95%. This indicates the test has a 95% sensitivity to detect a specific effect in the study when the effect is present. So since the power is to be 95%, this is indeed right. So when the statistical test has a power of 95%, it means that it has a 95% of chance of correctly detecting true effect or true difference in the population. So this thus talks about 95% sensitivity. So it is true. Okay, so this question asks a clinical trial was conducted which obtained statistical significance. The effect size was measured to be 0.19. Since the effect size was measured to be so small, we would conclude the result to not be particularly significant, regardless of the potential impacts of the study. So effect size does tell you how meaningful the relationship is, the relationship between the variables. So the higher effect size will tell you that the research finding has particle significance, while a small effect size, like in our case, it will tell you it has limited practical application. But it doesn't necessarily mean that it's not particularly significant. So the question does look like it is true, but it is not indeed, because it's not particularly significant. You can say that it has limited practical significance, but you cannot say that it is not particularly significant. So the answer is false. Question 2.1. Which of the following statement is accurate regarding the hypothesis test? Let's evaluate type 1 first. Type 1 error can be considered as the rejection of the null hypothesis when the alternative hypothesis is true. Okay, type 1 error is, by the definition, type 1 error occurs when the null hypothesis is incorrectly rejected, which is right for the first part, when it is actually true. So it's not the alternative hypothesis is true. It's the null hypothesis is true. So A is not right. So B, okay, power can be considered as a probability of rejecting the null hypothesis. That is right, when the alternative is false. So the power can be considered as a probability of rejecting the null hypothesis when the alternative is true. We are interested in whether the alternative hypothesis is. We are technically interested in whether the null hypothesis is false or not, but our true interest lies in the alternative hypothesis. That's the one that we really want to solve it. So the power is basically, by definition, it's the probability of rejecting the null hypothesis when the alternative is true. So this is not right. So C, when the probability of type 2 error decreases, power increases. Yeah, type 2 error decreases. So we're going to look at the D first, because I think D talks about the type D error definition. So let's look at that. Type 2 error. Type 2 error can be considered as a rejection of the null hypothesis. Okay, when the null hypothesis is true. Okay, so type 2 error is, by definition, if the investigator fails to reject, so it has to fails to reject the null hypothesis that is actually false. So it's wrong on both sides. So type 2 error can be considered as failing. You'll just write failure to reject the null hypothesis when the null hypothesis is false. So this is wrong, because it's just written wrong for the definition of the type 2 error. So D is not right. And then let's look at C then. So C is saying probability of type 2 error decreases when the power increases. That is right, because the probability of type 2 error decreases, the power of the test increases. This is because that the probability of failing to reject the null hypothesis when it is false implies an increased ability to detect true effects, which is what the power means. So the answer for this question is indeed C. Question asks, in a pharmaceutical study to develop a new pain relief medication, researchers investigate two factors, dosage and administration method. Dosage has 3 levels, like low, medium, and high. And the administration method also has 3 levels, oral, tablet, injectable, and transdermal patch. Okay, the response variable is the pain relief, 1 to 10, and how many treatment groups result from the combination of these factors. So it's asking number of treatment group, and since we have 3 dosage levels, that is 3 times 3 administration methods. So 3 times 3, which is 9. So the answer for this question is 9. So C. So D. Okay, let's look at this question. In a statistical study, which of the following statements could describe the relationship between confidence interval, margin of error, sample size, and confidence level? Okay, let's look at option A. While keeping the confidence level constant, okay, increasing the sample size decreases the margin of error. That makes sense. And which narrows the confidence interval. So that is right, because if you have more sample size, it will decrease the margin of error. And if you decrease the margin error, that will narrow down the confidence interval. So let's look at the option B, C, D, Y, and see why they're wrong. So B, increasing the sample size increases the confidence interval, which narrows the confidence interval and reduces the margin of error. You might think this statement is right, because it does talks about the narrowing the confidence interval and reducing the margin of error. However, it says it increases the confidence level. So regardless of the sample size, the confidence intervals will not change. Confidence level will not change, not interval. Confidence level will not change. So this shouldn't have said it's increasing the confidence level. You can say narrowing the confidence interval and reducing the margin of error, but not the level. So B is not right. Okay, let's look at C. While keeping the confidence level constant, increasing the sample size increases the margin of error. If you have more sample, then it has, lower chances of making errors. So that is not right. So it decreases, which is not right. So C is not right. And also it's not widens, it's narrowing. So also that part is wrong. Okay, let's look at option D. C, increasing the sample size decreases the confidence level, which widens the confidence, blah, blah, blah. So it's not decreasing. It should have said it doesn't change. So D is also not right. So the answer is A. If you see this kind of question in the exam, just look at whether the confidence level is increasing or decreasing. That will get rid of B and D. And then all you have to think about it is just A or C. And then if you think about logically, if you increase the sample size, this will decrease the margin of error, because there's less chance of making errors, and then which will narrowing down the confidence interval. So the answer is A. So you can logically think through. And just remember, confidence level does not change depending on the sample size. Okay, this question asks, the local environmental task force is conducting a study to estimate the average CO2 emission. A simple random sample of 22 vehicles was taken, and the data is collected. And the following 2 graphs are histograms and normal probability plot. Okay, using the above provided figures, what specific assumption about the data can be tested? And please explain your answer and be clear about what information is conveyed in each graph. Okay, so both the histogram and probability plot provide about the possible shape of the population of CO2 emissions, whether they're skewed or not. So let's look at that. Let's look at the graph. So histogram, the blue curve and the red curve looks like having a longer tail in the right side, right? So this side is longer. Normally, if it's normal distribution, it would be more like looking like a bell curve. So center is at the middle and the right and the left are about the same length. But if you look at our graph, the right tail is longer. That means this is positively skewed. So you can say the histogram shows that that it is positively skewed. Yeah, sorry, my handwriting is not great. Positively skewed and not a symmetric distribution like a bell curve. And this tells us that and let's look at the normal probability plot too. This same behavior is actually seen in the normal probability plot. So if you look at the graph, so the plot above the line at the end is above, right? And then below the line in the middle, if you look at that. So you can also mention that the normal probability plot shows that the points are above the line at the end, and below in the middle. This also indicates that it is positively skewed. So the data is positively skewed. So the assumption of normality is not valid, especially with the small size of random sample. And let's look at the option B. So if the assumptions mentioned in A are not met, how could you adjust the data to potentially satisfy these assumptions? If your answer to A is affirmative regarding the assumptions, specify any additional assumptions required for the analysis that cannot be determined from the graph alone, and explain how you'd verify their validity. So assumptions. So in our case, it's not met. So when the data is skewed, what statisticians usually do is perform the log transformation. If you apply the log transformation, it will make it more closer to a normal distribution, which is why it's a common practice. So apply the log transformation to make it more closer to a normal distribution. Question: ask a company exclusively employs 22-inch cube-shaped boxes for shipping, blah blah blah. So, however, the executive responsible for negotiating the shipping rates held the opinion that the mean weight was above 50 pounds. Okay. To further investigate this matter, the executive selected a sample of 45 boxes. The sample yielded a mean weight of 50 point blah blah blah, and the sample standard deviation of 0.1083. And then, does the data offer any evidence supporting the claim? Using this information and use the four-step hypothesis with a significance level of 0.09. Okay, so let's look at our output numbers, which is all the way at the bottom. Okay, so let's see. Yeah, this is all of those, right? I'm gonna copy that image and then put it in here for reference. Let's do that. Okay, this is very tiny, I know. So if you look at our output, let's see. So output is saying it's two-sided, less greater, two-sided, less greater. Okay, so we're given that the mean was around 50, right? So it's not mu is 0. So output 1, 2, 3 is not right. So it's going to be either 4, 5, 6. Two-sided, less, greater. And if you look at our option, the executive responsible for negotiating held the opinion that the mean weight was greater. That's your alternative hypothesis. Not a higher hypothesis. There we go. Alternative hypothesis. Greater. So it has to be greater. So the only option left is C. Not C. I'll put 6. So output 6 will be our hypothesis test, and then in step 1 you have to first define the parameters. So define parameters. So let's do mu of box as mean weight of boxes filled at this company for shopping. Okay, now in step 2, you have to state the hypothesis. There we go. So H naught. So mu of box and HA. So our alternative hypothesis, we know that it has to be greater. So it's going to be greater than 50 for our HA alternative hypothesis. And the null hypothesis is the opposite of alternative. So it's going to be less than or equal to 50. Okay, cool. So now it's asking to, in the step 3, you usually do, calculate and state degrees of freedom, test statistics, and p-value. Okay, let's do degrees of freedom first. Degrees of freedom is usually n-1 for the t statistics, right? So t statistics has a sample size of 45. So 45 minus 1, which is 44. So we have degrees of freedom of 44. We have that. Okay, that's good. And then let's look at the test statistics, which is already given for you in the output 6. So t value, you just have to write it down. It's 2.3595. Okay. So p value, are we given that? Yeah, we are given. Yeah, of course we are given, because we have to refute whether we are going to reject or accept the hypothesis. So anyway, so we are given, so it's going to be 0.0114. That's the p-value. So we stated all values, right? Degrees of freedom, test statistics, p-value, we have all. Okay, now we have to decide whether we're going to reject or not. So the p-value, we calculated, or we're given, are 0.0114, and then that is smaller than 0.09, right? So if the p-value is smaller than the given p-value, given as like the significance level value, we say that we are rejecting the null hypothesis. So in conclusion, the data does provide some evidence, p-value 0.014, to the claim that the population average weight of the filled boxes, this is supposed to be weight of the filled boxes, is greater than 50 pounds. So that's your conclusion. So this question asks to calculate an appropriate confidence interval or bound that corresponds to the hypothesis test conducted in part A. And state if you're using a confidence interval or bound, and be sure to mention the confidence level, etc. So if you look at our alternative hypothesis, was this, right? I'm going to copy paste this value. So since the alternative hypothesis was greater, we are going to use confidence level bound. Confidence lower bound, sorry. Yeah. Because we have the greater sign for the alternative hypothesis. So confidence level, how do we calculate the confidence level? It's the 100 times 1 minus alpha. Our alpha is given as 0.09. 1 minus 0.09. That gives you 100 times 0.91. So this will give you 91%. Okay, so critical value. So critical value can be found by the back of the booklet we are given. Let's see, where is it? Output 7. I'm just going to copy paste this value. Where's the question? Here you go. There we go. It's small. I'm just going to zoom in. Okay. So we have this value, output 7. So we know that the A value is 0.09, right? And it's not like it's divided by 2 because it's one-sided. It's not two-tailed. So yeah, we have that. So it's not going to be those two, not those. So it's going to be either this or that. And lower tail is whether true or false. And also this is not right because we need to include the degrees of freedom. So it's not those. So it can be either this two, and it's asking whether the lower tail is false or true. If the lower tail is true, that becomes the left side. But we're interested in the part that's greater than 50 for our alternative hypothesis, which is why we're going to be using lower tail equals false. Because if it's true, then we're going to use the left side. But we're interested in the right side. That's why our QT value is 1.362417, which has the one that has lower tail equals false, 0.09 df, and QT. Wrap it around. I'll just move that. There we go. Yeah, and then you have to calculate the lower confidence bound now. Lower confidence bound equation is the mean value times t statistics value and then standard deviation divided by square root of the population or the sample size. Yeah. Is 50 the population? Wait, 45 is the sample size. There we go. Yeah, it's the sample size and not population. There we go. So the sample mean, we are given that sample mean is 50.0381. Okay. 50.0381 minus t statistics value, which we found in A, was where is it? Oh wait, no, it's not A, from B. I mean, yeah, 1.362417 times the standard deviation value. Okay, standard deviation value is 0.1083. Okay, and then the n value, the sample I guess size, which is 45. So square root of 45. Okay, if you do this, if you just punch it into calculator, you'll get something like 50.016. So that's the answer for this question. So that's all you need to answer for part B. And let's look at part C. Interpret the results obtained in part B within the context of the problem. Okay, so we found the confidence level is 91%. So we can say that we are 91% confident that the true mean weight of the boxes is more than 91%. Confidence lower bound of 50. What was it? 016. There we go. 50.016. So that's all you need to write for the C. We have to say the value for 91% and we have to say it's 91% confident and mention something about the confidence lower bound value and the greater than 91%. Number 5. A group of dietitians conducted a study to investigate the impact of consuming pasta with and without a source of protein, and they collected an SRS of 50 participants and randomly assigned either to group 1 or 2 until one group reached the size of 25. Okay. During the experiment, all the participants were on an identical, strictly controlled diet for 1 week. At the end of the week, Group 1 was given a meal consisting of pasta with additional source of protein. Okay, and the Group 2 was given the same dish without any protein. And blood sugar levels were measured for each participant both before and after, and the difference were recorded. The summary statistics is the below. Okay, so part A. Considering the study's objective and the method of data collection, which statistical methodology between two sample independent and two sample paired would be more suitable for analysis? For this question, I'll go with two sample independent. The reason why is group 1 had a protein and group 2 did not have protein. So they are collected independently. So whatever they do in group 1 didn't affect the group 2. If it does affect, then it will be paired. But since it didn't affect it to each other, to each group, I'll go with independent. So it doesn't affect group 2. So I will just say, okay, if one person from group 1 does not affect another person in group 2, because they have nothing to correlate whether having a protein or not having a protein. So that's why I'll go with two sample independent for this question. And let's look at part B. The researchers would like to know whether eating pasta with a source of protein reduces the rise in blood sugar level compared to eating pasta alone. They have a set of significance level 0.05, state a null and alternative, and then use the same order of subtraction as in the table. Clearly define the parameters used in the hypothesis. Okay, let's define the parameters first. Parameters, I'll just do G1 as group 1 is the average difference in the blood sugar, my tongue twisted, levels after eating pasta and before eating pasta. And UG2 is the average difference in blood sugar, fast difference in blood sugar levels after eating pasta and then before after eating pasta. And this group 2 actually had right. Oh yeah. Okay, group 2. So okay, right. So group 2 was the one that didn't have the protein. So they have the average difference in blood sugar level after eating pasta and before eating pasta. So I should have added that pasta was an additional source. Sorry. And with an additional source of protein. So yeah, that's group 1 and group 2. So H naught would be UG1 and UG2 would be equal to, actually what is the, oh yes, I'd like to know whether eating pasta with a source of protein reduces the rise and compared to eating pasta alone. Okay, So if you want to reduce it, then UG1 minus UG2 has to be greater or equal to 0. So it's increasing or equal. But then we're interested in reducing the level, so the difference has to be less than 0 to reduce it. So UG1 minus UG2 is less than or 0. Okay, there we go. This question asks to evaluate the p-value basically. So we're in the above, we figured out our alternative hypothesis is less than, right? So if you draw the normal curve, that is looking weird. Anyway, I'll go draw it here. So the normal curve is like this. And then if you're interested in to the less than or 0, 0 would be this part. And then, so if you're interested in the less than 0, meaning we'll be looking at the lower tail equals true, which all of them are lower tail equals true. That's great. And since this is one-sided, you don't have to do the 2 times, statistic value. So not B and C. So it's going to be either A or D. But if you remember the degrees of freedom value for the two sample case, it is N1 plus N2 minus 2. So N1 was 25, the sample size, and then N2 is also 25. So it's 48, which is closer to 47. So the answer for this question is D. So now let's move on to A. I mean, not A, but 2. Select the correct decision based on your choice of p-value. Our choice of p-value is 0.018. 0.018, and the given sample significance level is 0.05, which is less than, right? So since the value of p-value is less than the significance level, we're going to reject the null hypothesis. Okay, let's move on to D now. At 95% confidence, what is the choice that is compatible with the hypothesis given in part? Confidence level or confidence interval, lower confidence bound, or upper confidence bound. So since our alternative hypothesis is less than sign, we are going to use upper confidence bound. Okay, and then part E. How does 0 relate to your selection in part C? In other words, if you opted for confidence bound, yes. Is 0 positioned above or below the bound? Okay. So in our case, the true mean difference between the change in the blood pressure, I'll write it down. Yeah, the true mean value difference between the change in blood pressure and blood pressure, blood sugar, right? It's not pressure. Blood sugar level of those with protein and without be bounded above by a negative quantity. And it's above by a negative quantity because we rejected the null, the H naught. So since the 0 is the value that distinguished the the left side or the right side of the distribution, so the 0 would be and also 0 is, okay, never mind, yeah, sorry. So since our null hypothesis was UG1 minus UG2 is greater or equal to 0, but then we rejected the null hypothesis. So using the confidence interval, which was 95% from question D, so 0 would be above the confidence upper bound. Right. Because we reject, the reason that it is above is because we rejected the null hypothesis. So that's it for the question 5. Okay, this question asked, let's see. The component is a well-established process for producing this component and has been measuring the standard deviation, which population standard deviation is 2 nanometer. Okay, and you can read the rest. The current critical dimension is measured to be on average 22 nanometer. And for a new technique to be worth the investment, they need to have an average reduction of 2 nanometer to justify. A study is conducted and the significance level is 0.001. Okay, we have that. And then additionally, the study requires a high degree of power to detect a reduction of 2 nanometer or more. The team working on the improved lithography technique is granted enough resources to manufacture 35 components, which is the sample size. Okay, so this question, you can go in 2 different ways. You can either do 1 sample procedure or 2 sample paired procedure. So I'll just write 2. So 1 sample would be using the parameter like U of something like U of CD or something, and then have that as the true average of the critical dimension. And then we can have H naught as U of CD is greater or equal to 22. And then since we're interested in the reduction, we're going to do U of CD is less than or 22 for the alternative. And if you do 2 sample, so the parameter would be U of D. So the 2 sample, what I meant for the 2 sample is if you consider the company will produce 1 item with and without the new technique, we can consider this as a pair procedure. So we're going to use the U of D as the true average reduction in the dimension. So we can have H naught as U of D, which is greater or equal to 0, because we're interested in the H naught to be less than or 0 to reduce it. So alternative would be U of D less than or 0. We can do that. So that's A. So let's look at B. So since this is one-tailed, so not two-sided, so it's not going to be divided by 2. Okay. So that leaves with us either this one or that one. Okay. And since we're interested in the lower value, it is false. That is indeed true. And the p-value, okay, p-value is gonna be the significance level. So that's this one. So yeah, so the p-value is 0.001 because we are given. So it's going to be 3.090232 for the corresponding critical value. Okay, and then I can solve it in 2 different ways for the cutoff. So if you do the 1 sample version, the cutoff would be the mu naught value minus C value times sigma and then square root of n. So which mu naught value is 22, right? Because that's the current critical dimension, minus which C value is this lovely thing 3.0920232 times sigma value, which is we're given as 2, right? and then square root of n, so n value is 35, so square root of 35. So if you calculate this, you get something like 20.955 or something like that. And then if you do two sample paired, like the one that I did above, sample, I cannot spell, I guess, paired. So x cutoff would be u naught minus c times square root of sigma over square root of n. Yeah, c times sigma over square root of n. There we go. So mu naught value would be 0, right? And then minus 3.09232 times what is the sigma value? Yeah, 2. I forgot. Oh well. And then square root of 35. There we go. If you do that, you get something like negative 1.045, something like that. So those are the ones that you want to find for the x cutoff. You can do one way and then stick with it. You don't have to find two. I just explained it too in case anyone is interested in doing that. So let's look at problem C. So utilize the cutoff value evaluated and calculated in part B to calculate the power associated with detecting a decrease in the critical dimension by 2 nanometer. Clearly show the mathematical steps and select the correct output. Okay. So if you do the one sample one, yeah, I'll just divide it into two sample. Okay, if you do the one sample one, computing the power would be 1 minus beta, right? So the power is 1 minus beta. And so the p value we need to find is x bar is less than the value, what was it? 20.955 minus mu naught value 20 divided by sigma divided by square root of 35. This is how you find the z value, right? This is, so it's like x bar is mu what is it? I guess so x cutoff minus mu over sigma over square root of n. There we go. That's how you find the value using the C table. So C is less than or equal to something like, if you do this calculation, this just becomes 2.825. And then if you look at our options, we have this one, 0.99766422. So that is the output that you're going to choose for one sample, right? And then if you do the two sample one, if you do that, I will just write it down for this one actually. Okay. And we chose, I think I'm going to go back to actually and explain it more. So we chose this one, like the one that is like a squared. We chose that one because it has the 2.825 value, like this one, and this one also has it, but then we're interested in the lower value, right? Because our alternative hypothesis included the less than sign, which means we're interested in the left side, right? So, and left side is only including when the lower tail is true. If the lower tail is false, that would be the right side. So that's why we choose this a squared one. So it's 0.9976422 value. Okay, cool. And then two sample paired. Let's do that. Two sample paired. So for computing the power, you use something like x bar is less than, what is the value, that negative 1.045, which is equal to 1 minus beta. That's the power equation. You just have to kind of remember power is 1 minus beta. So, yeah. And then if you standardize it, it's the same logic like this. So x cutoff is less than negative 1.045, and then plus 2 because mu naught. Alternative hypothesis is, if you remember, it's a mu a value. If you go back, addition of the study requires a high degree of power to detect a reduction of 2 nanometer, which is why we are going to use mu naught as negative 2, because we are reducing one. So negative 1.045 plus 2 instead of negative. I mean, it is still negative, but if you plug it in x cutoff, so x cutoff minus 2, that just becomes positive, right? So that's why it just becomes plus 2. And then plus 2 over 2 square root of, oh boy, there we go. 2 square root of 35, because we have the sigma value as 2 and the m value as 35, so you just plug it in. So if you punch it in, this is the standard deviation, so z value less than 2.825 if you punch it in the calculator. So then, if you look at the option choices, this is still the same value, right? Because we're interested in the lower tail. The z is less than. So lower tail is true, and the 0.9976 for 2. That is the interested our p-value. So we have that for C. And I think that's it for question D. Yeah. Question is the extra credit question, so if you don't want to do it in your exam, you don't have to. But since we have it, I'll just go over it. So a two-sample independent analysis is conducted by a researcher who decides to use the pooled estimator of the variance to construct 95% confidence interval for the difference in means between population A and B. And we know that the variances of A is equal to 25 times variance of B. Okay. And then if the confidence interval is built using a sample from population A and from B, what can be said about the width of the confidence interval and the true coverage probability of the confidence interval? And the formula for the pooled estimator of the variance is given as x squared p value. Okay, so if you look at it, NA plus NB minus 2 is all in the same terms, right? So this value would be, you can ignore this value because we're dividing the same value anyway. So this is not the important part. NA value is 825, so this is 824 in here. And then MB becomes 45. And then S squared of A and S squared of B. So S means the standard deviation, right? SD. Okay, yes. S means standard deviation. And you might think we're not given the standard deviation value, but if you recall, a standard deviation is the square root of variance, right? So, and then we're given variance of A is 25 times square variance of B. So A value is bigger, right? A value is bigger. Variance of A value is bigger than variance of B value because 25 times bigger. 25 times of variance of B is variance A. Okay, we know that. So since the variance of A is bigger than I'll just write it here. Variance of A is bigger than variance of B, and the population size is also bigger. This will make the width of the confidence interval wider than the average. So if you say that is wider than the average because of the variance, then indicating the true mean difference more than 95%, right? That is right. Since population A has a larger variance, it influences the width of the interval. That's why making it a wider on average. And if you make it wider, the true mean difference between the populations more than 95% of the time which indicates that option D is the right one. And if we go to the next question, it's asking for a two independent sample procedure. Provide a scenario where using the pooled estimator may be advantageous. Explain why this approach is beneficial in that particular situation. So the estimator would be advantageous when the variance value would be the same. The reason why it will be advantageous is that we can pull both sources information from sample A and B to estimate the quantity and pull the info together. Yeah. Such situations we get a more efficient estimator than the non-pooled estimator like the above. So that is why it can be advantageous. So that is it for the extra credit question, and I think that's it for the exam as a whole.